Okay, so welcome to another recording for Math 9. Our concept today will be similar triangles. What makes a triangle similar? Pretty similar to the things that make any shape similar. It's all about angles and proportional sides. So with no further ado, let's get on to it. Similar triangles. I'm going to look at these examples right here on the bottom. What we want to do here is draw triangles that are similar to the triangles that we see here on the page. And to do that, you're going to need a ruler and a protractor. So here we have a triangle with three different angles, a 70, a 50, and a 60. Then we have this one here, a 3, a 2.5, and a 2. And we have this one here, GH, HJ, a 2, a 3, and whatever the length of the side here is, we can measure. And it's got one known angle. I thought we'd work with, let's see. Let's work with the middle triangle here, 3, 2.5, and 2. So I'm going to enlarge it by making one side, doubling each side, 3, 2, and 2.5, and also by doing the appropriate angle measurements. So, grid paper, line paper, doesn't matter much, whatever you prefer. You're going to use line paper and a centimeter ruler. Now, if you look back at that middle diagram, the straight side is 3, so if I want to double that side, I'll make it 6. Now I need an angle measurement here. So I'm going to go to that shape and measure angle E down at the bottom here. $30 degrees. It's a 30-degree angle. So going back to this now, we're going to go here and we're going to mark it at 30 degrees. So now we know the slant of our line. The bottom, the measurement of this part of the triangle is 2 centimeters. So all I have to do is align my ruler with this mark here and the end point here. But then don't make your line all the way up, just make your line 4 centimeters long because it's 2 and we're doubling it. So you really only have to measure the one angle. This side was nice and straight, so we did that. Measure the angle down here. And because this one was measured correctly and this side remained proportional from a 2 to a 4, all I have to do now is simply connect. And my best indicator to show that I did this correctly is if this side turns out to be 5 centimeters. And you can see it does. So we only needed to really find the measure of one angle to do this particular enlargement. Let's try another one. Let's do Yeah, you know what? One example should be fine. So we enlarged the middle triangle, the one that was 3, 2.5, and 2. That was DEF. And let's just indicate that this was on page 343. Yeah, there's no need to do a second example of this, I don't think. There'll be similar examples coming up. So the next part of this you know what? I think we should probably enlarge. Yeah, we'll enlarge another one. We'll enlarge ABC. Sorry for being so indecisive. But anyways. ABC, we're going to do a measure of the straight side on top, because that's the easy one to start with. 3 centimeters. So I'm going to make it 6 straight across the top. And I'm going to make this triangle over here. And now the angles are given, right? So we know that this angle here is a 70. So we simply put our protractor here and we label it 70. Now what's the length of that side going down? It's 3.5. So on our sketch here, it'll be 7. Don't go all the way, just 7 centimeters. And as you can see, you don't really need any more angle measurements. Now you can just connect. We have a 70 up here. That's a 7. And let's just measure that one remaining side, side BC. It's also 3.5. So it would follow that this side is 7, and it is 7 centimeters. So 6, 7, and 7. Let me look at that side again. It's a little more than 3.5. So this one is a little more than 7. That's about, I would say it's almost 7.5. We'll call it 7.4. And then we have the 2 angle measurements that we already had, which is a 50 and a 60. If this had been 7, 6, if these 2 sides had both been 7, you'd have an isosceles, and then these 2 angles would have to be the same. That's why I was double checking. And yeah, it's a little more than 3.5, the measurement. So this side is a little more than 7 when we enlarge it. And otherwise, there'd be an error in my drawing, because if these are the same, then those angles here need to be identical as well. That's how an isosceles works. Doesn't work any other way. So, let's write down a definition now that we've done this part. Right below here, let's write down a definition of similar triangles. So, when triangles are similar, all angles are equal, and corresponding sides are proportional. In other words, if the original side is 3, then the new side is 6. That's double, right? Proportional. These two triangles were all enlarged with times 2 by doubling. That means they're proportional. They could have been enlarged by tripling, or they could have been divided. As long as each side was multiplied or divided by the same number, by the same, we call the scale factor, of course, then they are proportional. All right? Let's take a look at another example. Page 344. We're going to start there. Here we have two triangles with corresponding angles all equal. 62, 43 down on the peak, 75. This triangle is simply shifted, so this is here, it would be the top of this one. It's the same, right? And if we measured the sides, we'd find that they are proportional. We can measure one side. We'll do the one here with the 62 and the 75, and then here, RQ and BA. 2.5. This side is 3, so it was multiplied by a very small scale factor. Let's just check what that is. 3 divided by 2.5, 1.2. So as long as the entire shape was multiplied by the same scale factor, .1 or 3.2 here, and then 4.2. So if I take 3.2 times 1.2 here, I get something very close. So, and these drawings aren't always perfectly accurate, but you get the point. The angles are the same, so the sides are proportional. Let's have a look at page 345. We have this diagram here. Are the sides proportional so that we can say the triangles are similar? We can see which sides relate to each other. 6 and 4, right? 7.5, the straight part, and 6, and then the slanted 6 and 9. So let's check all these. So example on page 345, we simply do the 6 and the 4 matched up. 6 divided by 4 is 1.5. The 7.5 and the 5 matched up. Check that. Also 1.5, and the 9 and the 6 matched up. Divide that. Also 1.5. So we have a scale factor of 1.5, or 3 over 2 if we do it as a fraction. Let's have a look at pages 346 and 347. Now we're going to have two different examples, a totem pole and a lake. Let's read the question here. At a certain time of day, a person who is 1.8 meters tall, over here, has a shadow of 1.3 meters, over here. At the same time, the shadow of a totem pole is 6 meters, over here. The sun's rays intersect the ground at equal angles. How tall is the totem pole to the nearest tenth of a meter? So this is our unknown here. So we can use a proportion from the person's shadow to find out the height of our totem pole. We're doing an enlargement to do this one. So page 346, the totem pole. Take the person's shadow. Person, their actual height is 1.8. Their shadow is 1.3. So 1.8 divide by 1.3, 1.38. How do we then find the height of the totem pole? Well, we know the totem pole shadow is 6. And it's an enlargement, so 6 times 1.38. $8.28 or 8.3, if you want to round it up, is the height of the pole. And that's exactly the answer they're saying. They have a slightly different decimal, but that's just a case of how they rounded it. Let's now look at page 347. Using overlapping triangles to determine a length. A surveyor wants to determine the width of a lake at 2 points on opposite sides of the lake. She measures the distances and angles on land, then sketches this diagram. How can the surveyor determine the length of HN to the nearest meter? So she wants this length right here. And she has these two lengths. She split this off into 2 triangles. So what you do is, you look at this as having 2 separate triangles. You have a small one here, this one. Then you have the big one that also encompasses the small one. And you simply use this information to find out. So, the length of the big side, find that by adding the 2 together. Then divide it by the short side. There's your scale factor. So, this will be page 347. Lake, similar triangles. I could have said overlapping triangles. But anyways, so the length of the 2 sides. 305 add 210 is 500. 515. 515. That's the length of the long side, the entire long side. Now, to find our proportion, remember that short side, that's 210 from here. 515 divide by 210. 2.45 is our scale factor, shall we say. So then we're dealing with an enlargement here. Let's look back at our diagram. If my scale factor is 2.45 and I have 230 meters here and I want to find this enlargement here, I'm still dealing with the same diagram. So all I have to do is 230 times 2.45. Got my scale factor. 563.5. Or 564 rounded up, which is exactly what they have in their rounded answer. Okay, a bit of homework on this concept, and then also the mid-unit review. So I'm going to go over both of those. Let's first of all do your homework on page 349 to 350. Do this before you do the mid-unit review. 349 to 350. Numbers 4, 5, 6, 7. Let's have a look at those. So 349 to 350. Numbers 4, 5, 6, 7. Number 4, simply identify which triangles in each pair are similar. And if they're not, how do you know? Well, obviously the first example here, the angles are all the same. No brainer. This one, there's no angles. Better check if the sides are proportional. If they are, they're similar. Okay? Number 5. In each diagram, identify two similar triangles. Explain why they are similar. Okay, so here, obviously, once again, we have the case of the equal angles. Here, do we have proportional sides? It looks like we do. And here, we have, if this is that looks like we have equal angles. That's a 66, that's a 66, so it would follow that this one, and there's a 39 down in the corner, so we have, again, equal angles, and if we were to measure the sides, we'd find they're proportional. This is the same as that lake problem, by the way, if you haven't noticed that. Determine the length of AB in each pair of similar triangles. So AB is here on top. We don't know what it is, but we know that it corresponds with DE, and DE is 12. So we look at what matches up. We've got a 5 and a 10. We must have a scale factor of 2. So it becomes very simple then, right? 12 divided by 2 is 6. Number 6 continues on page 350 with similar things again. Length of AB is here. Find out what the scale factor is. Find out which side matches up with AB. And find AB. Here, similar to the lake example, we're finding the long side of the top of this triangle. See? And finally, number 7, similar to the totem pole example, where we have a person and we have this side, and we are looking to find how tall is the flagpole instead of how tall is the totem pole. So your homework for this lesson is very, very similar to the examples that we did. Shouldn't give you any fits. On to the midterm review. We'll find this on page 352, mid-unit review. And this will be then 1, 2, 3, 4, 5, 6. Which in fact means that we're doing all of them. 20 marks. Let's have a look at that midterm review. So mid-unit review on page 352, 20 marks. 1, 2, 3, 4, 5, 6. All the questions. It's all stuff that we've done. Reductions and enlargements. They're giving you a scale factor and asking you to find the new dimensions. And here they're telling you what the original was and they're showing you a drawing. So do the measurements, find the new measurements, and figure out the scale factor that they used. The original is here. This is a scale draw. Measure, and find out what their scale factor was. 3, copy this polygon on 1 centimeter grid paper. There should be some more of that on the table. If not, you can use 0.5 centimeter and just double it. It'll be the same thing. Draw a scale diagram of the polygon with a scale factor of 3/5. In other words, with a scale factor, if you want a decimal, if you prefer that, of 0.6. So you'll draw this and you'll enlarge it by 3/5 or 0.6. Here we have the top view of a swimming pool on 0.5 centimeter grid paper, and it's 60 by 40. Determine the original was 60 by 40 and they reduced it down. What is the scale factor? So they reduced it all the way down to, from a 60 by 40, they reduced it down to 3 centimeters by 2. So from a 60 meters by 40 meters, they reduced it all the way down to 3 centimeters by 2 centimeters. So what scale factor did they use to do that? These quadrilaterals have corresponding angles equal. So, are any of them similar? I hope you're not going to say no, because their angles are all equal. You have, each of them has a 70, each of them has 2 90-degree angles, and each of them has 110. So of course they're all equal. Okay? They are. They're equal because their corresponding angles are equal. It's just that simple. Then you choose one quadrilateral and you draw one that's similar to it. So pick any of these, in other words, and make an enlargement of it. Or shrink it, doesn't matter, bigger or smaller. Number 6. Just changed my mind about something, but we're going to talk about that in a minute. A window has a shape of a hexagon. Draw a hexagon that is similar to this hexagon and explain how you know they are similar. Right? So take this hexagon, draw it, and then you're either going to enlarge it or shrink it. That's up to you, but you're drawing a similar shape. Okay? Now, before we end this, I just changed my mind about something. We're going to skip 3 and 4 of the review because the same things come up again. You're doing enlargements and reductions here and here anyways. So we'll skip 3 and 4. So 1, 2, 5, and 6. And it's now worth 15 marks. So 352, 1, 2, 5, and 6, and it's now worth 15 marks. It just, it's a bit repetitive to do 3 and 4 as well. When you've done the same thing for 1, 2, 5, and 6. So, yeah. We'll leave it there. That's all for this lesson. There will be, I'm going to write this down. The next recording will be on Tuesday, so not till next week. Tuesday, April 28th. There should really be a class on Friday, but because you have that mid-unit review to work on, we're going to skip it, and we're going to resume this unit next week, Tuesday. So we'll skip the Friday class. All right? that will be everything.